Good afternoon from the U.S. Fish and Wildlife Service's National Conservation Training Center in Shepherdstown, West Virginia. My name is Ashley Fortune Isham, and I would like to welcome you to our webinar series that's held in partnership with the U.S. Geological Survey's National Climate Change and Wildlife Science Center in Reston, Virginia. The NCC-WSC Climate Change Science and Management webinar series highlights their sponsored science projects related to climate change impacts and adaptation, and aims to increase awareness and inform participants like you about potential and predicted climate change impacts on fish and wildlife. Right now, I'd like to take a moment and introduce today's speaker, Toni Lynn Morelli. After her PhD, Toni Lynn Morelli obtained the National Science Foundation Bioinformatics Postdoctoral Fellowship, collaborating with Steve Beisinger and Craig Moritz on an extension of the Grinnell Resurvey project. She continues these collaborations examining climate refugia under funding she has attained from the California Landscape Conservation Cooperative. She has worked for the U.S. Forest Service both as a research ecologist at the Pacific Southwest Research Station and as a technical advisor to the Democratic Republic of Congo. In her role as a USGS research ecologist for the Northeast Climate Science Center, Toni Lynn uses geospatial analysis, species distribution modeling, occupancy modeling, and population and landscape genetic techniques to facilitate natural resource management and habitat and species conservation in the face of climate and land use change. Currently, she is investigating how climate change is affecting boreal communities in the northeastern United States. Toni, welcome.
Thank you, Ashley, for that kind introduction, and I'm really happy to be here today and to see all of you participating in this great webinar series and for me to be a part of it. As Ashley said, I am a USGS research ecologist for the Northeast Climate Science Center, and the work I'm going to be talking about today is done in collaboration with a whole host of people, essentially two different research projects that I'll be talking about, so different colleagues from different places. And I want to be focusing on one particular aspect of climate change adaptation, climate change refugia. So here's a quick outline of what I'll be talking about today. Quickly go through how we know that climate is changing, and then generally talk about climate adaptation strategies, give an overview of that concept, and really be specifically drilling down into climate change refugia as an adaptation strategy in the conservation cycle framework that we developed. Finally, I spend most of my time talking about how to identify and test climate change refugia with a quick conclusion at the end. As we know, it is warming across the world and in most places and across most places in the United States. This is one view of that from the U.S. Global Change Research Program, that the most recent few decades compared to the first half of the 20th century have seen an increase of over 1.5 degrees Fahrenheit in a lot of places, including in the Northeast and in California, two places I'll be talking about today. And we know that those trends are expected to continue. So here's a view in the Northeast from work done out of the Northeast Climate Science Center by one of our postdocs, as well as Mike Rollins here at UMass. And it just shows how there's variation across season and warming, with majority of warming expected to happen in the winter and summer in the future. But this talk is not intended as a doom and gloom climate change talk, but one that hopefully gives you, I'm hoping that we can get some optimism and hope about what we can do about climate change, because we can look at these different species that we particularly care about, and you can think about whatever iconic species that you think of in terms of its relation to climate change and how it's particularly vulnerable, whether you're thinking about montane mammals or coastal birds or cold-adapted fish or human populations, particularly ones that are living at low sea level at this current point. And instead of getting overwhelmed, we can think about what are there climate adaptation options that we can help make these communities, populations, species more resistant to climate change. And I say resistant, in particular, I wanted to give a quick overview about climate adaptation options focused on what you can think of as the 3 R's, and this is work from harkening back to Connie Millar back 8 years ago and her colleagues, talking about how there are 3 major climate adaptation options: enabling response to change, promoting resilience to change, and creating resistance to change. And I bring this up because it seems more and more resilience is synonymous with climate adaptation, and this is a reminder that there are different ways that systems can be made more resilient as well as resistant, and as well as increasing the response. So, for example, you can enable response to change by promoting connectivity, diversifying seed sources and activities, or through translocation. Whereas you might promote resilience to change by forest thinning or restoration of inside stream banks, or even from a cultural resource perspective by making snow at ski areas in places that are warming. On the other hand, you might create resistance to change for resources in places that are particularly important, and you really just need to you want as holdouts as long as possible, including places like tribal lands where there is no opportunity for human populations to migrate. You could do this through fire breaks, intention removal of migrants, even kind of naturally shifting migrants in response to climate change, and just generally reduction in disturbance. Just to go on about this for one more slide, there was a recent paper out in Trends in Ecology and Evolution titled Viva la Resistance, and it's just, again, just a reminder that these resistance and resilience are different, related but different terms. So you can see here in RT, we have resistance, and this is the amount of ability for a system basically to stay in one way instead of shifting over to a totally different state. So you can see this is the amount that it takes until it shifts into a different state, given a disturbance. So on the left, you can see a disturbance like urbanization or wildlife or drought. And here's that system resisting. Once it changes to a different state, its ability to be resilient, so to come back to the original state. And NC here is net change. So once it is back in that state, how much has it changed nevertheless? Just some ways to think about that. And I bring it up because the rest of the talk will be focused on a resistance strategy, climate change refugia. And you can see that there are a variety of places in the literature where the concept of refugia more and more is discussed. This has become a very hot topic, especially in the discussion section of the literature said, kind of thrown out to say we should think about refugia and what it means for management. But very rarely is that actually analyzed in the context of that on-the-ground management or conservation. So a group of us got together to talk about this, and we had colleagues brought together under funding from the California Landscape Conservation Cooperative from across the western U.S. Scientists and managers and decision makers all wanting to think about how to operationalize this concept of climate change refugia. When I say climate change refugia, I mean areas that are relatively buffered from contemporary climate change that enable persistence of valued resources So note that we say contemporary climate change, so this is distinguish it from this process that's happened in the sort of paleontological concept, the long history concept. Those are obviously related, but we're distinguishing them here. And that we cast a pretty broad net. We're not just talking about refugia for populations or species, but valued resources, which can include physical and cultural resources as well as biological resources. Together we developed this framework, which we call the Climate Change Refugia Conservation Cycle, inspired by the Climate Smart Conservation Cycle of Bruce Stein and colleagues, that walks managers and conservation practitioners through step-by-step of how you would actually manage refugia on the ground. And I'm now going to walk you through that using examples from my research. And the first step is to define your objectives or your focus, and in doing so, you have to figure out what valued resource you're talking about. In this case, today, I'll be talking about montane meadows. And in case that you don't already know, montane meadows are important. They're important because they're botanically diverse. They're important to wildlife. They're critical to hydrological function. You can think about the conversations that are happening out west with drought, that they hold a lot of the snowpack that eventually trickles down to provide water to human and other biological systems during the dry period. And they are significant in terms of recreation and other economy. We also know they're particularly vulnerable for a lot of reasons, including those key hydrological functions with changing precipitation, but also because mountains are warming faster than other places. This is recent work from Ray Bradley and Henry Diaz in the Mountain Research Group, Initiative Group in Nature Climate Change. And this is just one cut. This is one mountain in Tibet, but they looked across mountains across the world and found that, in fact, weather stations at high elevations are showing that there have been faster increases at high elevations in recent times than there were historically or at low elevations. So that rate of temperature increase is happening faster. So we can think about how mountains are more vulnerable and meadows are important. And on that, how do we then manage montane meadows in this warming future? So step one is to define the planning purpose and objectives. And in this case, managers in our group defined a pretty broad example, since, again, this is just an example, and you could think about it for a more precise management unit. But this example is maintain montane meadow habitats in the Sierra Nevada with a 15 to 20-year planning cycle. Consider 50 to 100-year climate projections. So they wanted define the scope and identify focal resources, the study area, and the time horizon. The next step is to assess climate impacts and vulnerabilities. In a lot of cases, this has already been done, and some it hasn't. So you might have to then work with somebody to figure this out on your own, but you basically want to think about what your resource is vulnerable to. In a way, you can conduct a formal vulnerability assessment at this step. In this case, we considered that vulnerabilities and climate impacts included reduced moisture availability and precipitation, disruption of species synchronicity, vegetation shift, increased recreation impacts from more visitors and longer seasons. So we tried to kind of consider all of these different perspectives, how things would change. After that, you might want to review and revise your conservation goals and objectives. So in this case, we can go back and think, okay, well, we want to maintain sufficient montane meadow habitats to protect critical ecosystem services in prioritized watersheds. So those are our first three very general steps. And the step 4 here is really where we focus on the real methodology and theory even of refugia. And that is identifying and mapping key refugia features, considering scale and connectivity. And as you'll see, I'm going to give you a species-specific example. And it is important that in defining your planning purpose and objectives, you're thinking about what resource you're considering in terms of defining refugia. What are you defining a refugia for? And that might be that you're looking in terms of a particular history stage for a particular species. You might be thinking about ski areas. You could be thinking about particular seasons. So this is going to have particular attributes depending on what your focus is. So in order to identify climate change refugia, there's a couple different ways you can do this. And one of them is just to target refugial processes. And this way is actually pretty agnostic to your resource. So if you don't have any other information, you can just try to find places that are physical bases for climate refugia. So I'm going to walk you through these in the schematic. It's basically just a bunch of different ways that physical scientists think that climate might be buffered on the ground or in the water, and we've put pictures with them. So here you see topographically complex terrain creates varied microclimates and increases the likelihood that current climates will continue to exist nearby. So if you're in a very flat area, but with a little bit of topographic relief, you might focus on that topographic relief. Deep snow drifts provide insulation to the surface below and provide water later in the season. They also provide snow for species that might depend on that. Valleys that harbor cold air pools and inversions can decouple local climatic conditions from regional circulation patterns. One of the classic examples of climate refugia are cold air pools or icebox canyons, and that's what this is speaking to. Poleward-facing slopes and aspects, actually, simple as that, can result in shaded areas that buffer solar heating, particularly during the low solar angles of winter and early spring. You probably know this already. I mean, you may just not have thought about it that way, but there's a big temperature change just depending on which aspect you're at. Cold groundwater inputs produce local cold water refugia in which stream temperature is decoupled from air temperature. Areas near or in large deep lakes or oceans will warm more slowly due to the high heat capacity of water. And then finally, vegetation can drive some of this. So canopy cover can buffer local temperature maximums and minima throughout the year. So these are just examples of how you physically could identify places on the landscape that might act as refugia, even if you kind of know nothing else about what's happening there. There are other ways to identify climate change refugia. You could model stability based on recent or future climate. And with that, you need basically just weather station data or interpolated climate data. Again, it can be agnostic of your species or resource. And I'm going to talk a little bit more about that with an example. I'm also going to show you how we use the method of locating areas of high resource persistence or diversity. In that case is more of a case of being specific to the resource, and really often in this case we're talking about populations or species. So as I said, we used a couple of these methods to identify refugia, and we were specifically identifying refugial montane meadows in the Sierra Nevada under funding from the California LCC. I'm just showing this map again to remind you that California has warmed a lot in the last century and warmed even more in the last decade. And we know you can see from this figure that in the last year, in 2015, it was 3 degrees warmer. The minimum temperature was 3 degrees warmer than normal. It was the second hottest year on record. 2014 was the hottest year on record. Similarly, at the beginning of the year, it was a third of its precipitation and the second driest year on record. And you can see that represented here from Michael Mann and Peter Glick's paper. This is all California years, and you can see that 2014 was very high and hot and very dry. 2015 isn't on this map, but it would be somewhere out here as well. So again, we know that montane meadows are important, that they're warming, and the place that we are focused in is warming a lot. So we wanted to model, identify climate refugia first by modeling climate stability. So we got a map of meadows from colleagues at UC Davis, the ICE group. It started out at 17,000 meadows. By merging some of the smaller meadows, we cut that down to a much more manageable 7,000 meadows data set. And this work was done by Sean Marr, who's now at Missouri State, who was at UC Berkeley with me. And we then, working with Lori and Alan Flint, downscaled 800-meter PRISM data to 270 meters using their basin characterization model. And we looked at the difference in temperature and precipitation between the early 20th century and the late 20th century. We also looked at change in snow water equivalent and a couple other climate measures. So this map is of mean temperature, and I'll just be focusing on mean temperature for the rest of the piece. You can think, oh, well, there you go. You've identified your refugia. You have the map. Job is done. We can move on. But something I really want to focus on in this talk and keep on stressing, maybe proselytizing about, is that this is really just a hypothesis. In fact, mapping refugia is pretty rare. That map itself is a really exciting step that's hardly ever been done, so we were very happy to do it. But it's just a hypothesis, and we don't know that it is actually biologically relevant. And of course, there are issues with scale and all kinds of complications with modeling temperature and other climate factors. So we really wanted to see if the species on the ground were responding to these places that seem to be less changed in the way that we identified them. In other words, to test the predictive ability of refugia. To do that, we focused on the Belding's ground squirrels. One of the reasons we did is they are montane meadow specialists. We also, they're highly detectable, so we can conduct occupancy modeling, use robust survey methods. They live in groups in the diurnal. They're very easy to see, and you know when they're not there. We also had really great historical data on them as part of the Grinnell Resurvey project of the Museum of Vertebrate Zoology at UC Berkeley. We were able to go back to the surveys from the early 1900s that were done on the fauna of California and go back to the sites that were surveyed in the early part of the 20th century to see if the species was still persisting at these different sites. We could go back to the original field notes, and we could identify when they saw Belding eye and exactly where they were from maps and detailed descriptions, go back to those sites and see if they were still there. So I did this work with the great help of wonderful undergraduates and field assistants. We went, spent 2 years surveying the Sierra Nevada, trapping and doing visual surveys in more or less harsh conditions. And we were able to go back based on the kind of map notes I showed you and also these original photos that were taken, and know we were in exactly the same spot, like when we saw that exact cracked rock again 50 years later or 80 years later, to know that we were exactly surveying the same meadow that was surveyed historically. A lot of our sites are based in national parks or other protected lands, so we could be fairly confident that land use change wasn't a factor in any of the patterns we saw. So we went to 74 sites where Beldings had been historically present, surveyed as present. in the first part of the 20th century, and the resurveys were conducted in the first decade or so of the 21st century. And we had very high detectability, so basically if we didn't see the species, we knew it wasn't there. And what we found was that they had disappeared in almost half of the sites where they were historically present. An extirpation rate of 42%, which is pretty terrible for the buildings, but really good for us because we got a lot of data points to work with. I'm kidding, but we did actually get a lot of press out of this idea that buildings might be disappearing because it was a big surprise to people. In places where they're present, they're very abundant and considered a pest in agriculture. So we had some fun with some of the news articles that came out of this, including this, my favorite, evil cannibal squirrels could make California's drought less terrible. Because there are potential positive implications for buildings as a burrowing mammal and a really critical and a keystone species in these systems. They might be having an important positive effect on the hydrologic function of these meadows, which again are really important to downstream processes and water systems. So all this was to test this climate change refugia map. There's your reminder. That's what we're doing. There's the map. Very exciting, but we wanted to see if it actually meant anything to anybody. So we went back and looked at the data we had from where the buildings had persisted versus disappeared. So that's what these bars are. We've got a proportion of sites where U building I persisted. So you can see here, that's on the Y, and on the x-axis, these are basically just measures of change in climate. So we have got change in annual temperature less than 1 degree Celsius. So this is a way to define a refugium. Each of these, in fact, are a way to define a refugium because we weren't exactly sure what the species was responding to. So in that this means small change in temperature, you would expect if that is actually acting refugially for the species, you would see higher persistence than 50% or random. And that's in fact what we found. For each of these measures of refugia, we had higher persistence for the species. In some cases, much, much higher. The only exception was this change in snow water equivalent didn't seem to have any effect, or at least just a mild one. We also went and did just a one-time survey through Yosemite National Park to look at presence versus absence, occupied versus unoccupied meadows. And so you can see that map here, that red dots are meadows that were not occupied, blue dots are meadows that were occupied. It's not rocket science. Some of these are pretty low, but that in itself is telling us something. What I'd like to focus on especially is where there's exceptions. So this place here is not necessarily higher than this one here or warmer than this one here. And so what is happening with this place that the species is able to persist versus that one? And again, we found that it was correlated with change in climate over time. So when we had a change in minimum temperature that was less, and there was a smaller change in minimum temperature, species was more likely to be present. And this is, again, a change in minimum temperature over essentially the 20th century. Similarly, with species was more likely to be present in meadows that had a smaller change in annual precipitation. And here, snow water equivalent came out as predictive when there was smaller change in annual April snow water equivalent, which is essentially snowpack. The species was more likely to be present. We also did genetic analysis because we tracked at many of these sites to see if temperature was correlated with genetic diversity. And in other words, if we could see whether there was higher genetic diversity in climate change refugia, that would be an indication that those populations had been there longer. So you would expect higher genetic diversity, in this case our measure was allelic richness, would correlate with longer persistence. And that was, in fact, what we found, at least for one measure, that the lower the temperature, the higher the allelic richness. I just went through that step 4, so we can paste that map in here, and we can go on to the next step. And those are to evaluate and prioritize refugial areas for specific management. So I've tried to stress through my abstract and so far that this is a measure of a tool for prioritization. This framework is not to say refugia are the end-all be-all, but it's a way to decide, given your limited time, your limited resources, your limited staff, where you can put your management action. Where can you focus on the things you can actually do? So this is just one extra filter. Do they seem to be acting as climate change refugia? There's other things you're going to consider. So in this case, you're going to probably want to prioritize medium or large meadows over small ones that are highly connected over ones that are isolated, areas of high biodiversity, meadows where species of management concern exist or might exist in the future, areas of high recreational value if their uses are compatible. There's going to be other things you're going to consider, of course, always. The next step is to identify and implement priority actions to manage climate change refugia. So I suspect many of you might think, oh, this is what I really want to know about. But I think the answer is you know, at least my working with managers for the last 8 years or so, I've learned that most of you already know the answer, certainly more than I do. So here's what we got, our group, again, this group of managers and scientists working together. Here were some suggestions we were making. You know, minimize overgrazing, remove encroaching conifers and invasive species, again, if this is a resistance strategy, mitigate road and trail impacts, assist migration of lower elevation species, snow fencing to trap snow in desired locations, manage recreation and development, increase connectivity. Again, this isn't totally new, brilliant, off-the-charts science here, but hopefully it all being in one place is useful. And then finally, as every last step should always be, you know, make sure you're doing it right, and if you're not, go back and do it better. So monitor the effectiveness of refugia, realign objectives accordingly. So in this case, maybe you want to monitor meadow wetness via remote sensing and field measurements, monitor indicator species. And in this talk, I'm arguing that buildings can be acting as an indicator species, so you can go back and see, are buildings still there? Monitor downstream watershed variables, stream flow, sediment load, et cetera. I did want to just point out, as a last slide, give credit to Dan Isaac and the work that he's doing in the Pacific Northwest, which is wonderful. And it's based on cold water trout species, and they're doing really exciting work thinking about how these species are vulnerable to climate change and how they can be managed. So thinking about these cold water systems, and they've mapped them and are in the process of doing really great communication and thinking about networking up really good temperature data, really good information so that they can increase connectivity and manage these refugial networks. So really exciting stuff there, focusing on Salmonid. And there's this publication, but a lot of other work he's done as well. So in conclusion, climate is changing. Managing climate change refugia can be an important resistance option for climate adaptation. It's just one among many, but an important one, I think, to think about, particularly when there are resources that are just too precious to let go or to let change even very much. And there are a variety of ways to identify climate change refugia, but a lot of them are just hypotheses and should be tested whenever possible. So with that, I just want to say thank you to all the funders, California LCC that's funded most of this work, the Northeast Climate Science Center that's funding me to do this work, the National Science Foundation where we started this research off, all of our co-authors and my colleagues at UMass and with the Northeast Climate Science Center and all of my collaborators at UC Berkeley and field assistants who've helped with this. Here's the website, the general website for the California LCC, where you can find a lot of this information. You might be curious, that map that I showed, where your particular management unit falls out if you happen to be in California. And we have the maps that you can load up the rasters. They're all available. You can play around with them, look at it. They're all on that Climate Commons site. Just search for Morelli or for Refugia and you'll find them. And also plug in for the Northeast Climate Science Center site, which is fantastic. And with that, I'll take any questions. Great. So I see a question from Kelsey Jessup. While I recognize that each area may be different and have differing priorities, do you have a method of deciding what is precious to protect? Oh, that's such a good question. So this comes back to that valued resources definition, and frankly, it was a long, hard conversation in some ways to stick with that word value, but the managers in particular really stress the idea that everything we do is based on some value we're giving it. There isn't some fundamental quality except for what we're putting on it. That's a bit philosophical, but I think that for each management agency or NGO or citizen, everyone has a way to value things. And so people might be thinking, again, in this case, when we talk about meadows, you can think about the value of meadows for providing water to San Francisco, drinking water to San Francisco. And you might then prioritize finding refugio meadows in central the Sierra Nevada versus somewhere else, because that's where San Francisco is getting their water and that's what they care about more. Whereas if you're thinking about mountain yellow-legged frogs, you might be thinking more about places where there are fishless ponds and where the species moves through and needs an intact meadow in terms of a particular life history stage. So I think it remains for the person who's sitting at the table or the people who are sitting at the table to decide, and often it's not actually that flexible, right? It's either based on legislation, based on your job description, based on the, the office you're sitting on, what it is you're going to value and consider precious. I hope that answered your question. Alicia Grossa asks, regarding your finding that snow water equivalent, again, snowpack, wasn't correlated at the California scale, but was significant in the analysis in the smaller polygons. Do you have thoughts about this? Might snow water equivalent be a particularly difficult metric to get right? Great question. I'm very interested in. I would be happy to have people shoot me emails on this. I realize I don't have my email address on here, but you can find me at the Northeast Climate Science Center website. We do think snow is very important to this species. One reason also that it's a good indicator for these meadows is that it has very high overwinter mortality when there's no snow on the ground. So we think a lot of these extirpations are due to loss of snow, and then the animals actually freeze to death while they're hibernating. They go through all their fat reserves. There's no insulating snow blanket, so they actually freeze to death because of climate change, which is a fascinating story in itself. But we do think there's a close correlation with snowpack. But I think you're right. I think that it's really hard metrics to get correct. And so I think that it's kind of coming up as significant in some places and not others. And it's interesting that it came up as significant in our Yosemite study, but not as across the Sierra Nevada. And part of that may be that there's just very different elevations in the Sierra Nevada. And some places things warm and snow levels don't change, and some places it changes drastically. So that might be part of it. So Mary Ratnaswamy, hi Mary. So do buildings have any unique life history of physiological traits that might make them more or less vulnerable to climate change? Your genetic analysis is very interesting as well. Thank you. Yeah, so being hibernators, I think having this requirement to make it through the winter, in some cases 6 to 8 months of being underground, is a pretty, I think that makes them pretty vulnerable. They have to build up enough fat reserves in the beginning that they don't freeze out, and they can wake up, but if there's nothing on the ground to eat, that's not going to do it for them. So that's a particular trait. There's other ways that they are they're less sensitive to climate change, and they're given that they're rodents. They have some flexible life history strategies. They're omnivores. There's some, or they're not omnivores, but they have some habitat generalism. There's some flexibility that they bring, but they seem to be getting to pit surprisingly hard. Felicia, there's a temporal dimension to the definition of climate refugia. Do you see adding time to your conservation cycle in any way? That's a really good question. I'm going to pop it back up here. In step 1 here, you can see that we do say consider the time horizon, and we say consider 50 to 100-year climate projections. And we have a 15-year plan, 20-year planning cycle. So that was sort of what we were thinking a lot of managers think in that, from both of those perspectives. It is really important. And in fact, almost inherent to this as a resistance strategy is that you can't think about it in very long term because we just don't know what's going to happen. This has to be, in some way, a short-term strategy. And so it is important to kind of define your time horizon. There's 2 caveats to that. One is we don't know enough to know when these things are going to kind of become too warm or too dry, or in some cases, like some places in the Northeast right now, too wet to be relevant. The other thing is that we like to think about climate change refugia as places on the landscape, and although we want to test them out and think about them from a perspective of a particular resource, that might change over time. That doesn't mean the refugium is going to become totally irrelevant, but it might just be no longer useful for that particular resource, that particular population, that species, that ski area, you know. But maybe it still has some snow or is cold enough and still colder than the areas around it so other populations can move in. So we can think about this. It starts to verge into a longer-term horizon if you think about sort of moving targets, as this is still going to be a good place in the future, just maybe not for that particular resource. All right, well, thanks everyone, and I'd be very happy to keep talking to people and in fact help any of you brainstorm about kind of applying this and operationalizing this idea on your own management unit or your area of interest or for your particular resource of interest. This is very exciting and fun stuff. We're just at the beginning of it. So I hope this was useful. Thanks to everyone for participating, and have a great rest of your day and great holidays.